my bucket list that I've not been to yet in Arkansas. But this waterfall is not in Arkansas, but it is one state over in Tennessee. So the reason I'm showing you this is a picture I took. Fall Creek Falls is the area. It's around the Nashville area. It's the largest waterfall east of the Mississippi. Okay, so that's kind of cool. It's a 256-foot waterfall. So there's a lot of great hiking in this area, bike trails, if you want to take a bike out there, paved trails. And then there's 3 waterfalls in the area, and not that little small one over off the side. Three big ones, 3 good ones. So Fall Creek Falls is a really great area to go if you get out and branch out and go hiking at all in different states. Okay, I think I have some more Arkansas hikes to show you though before semester's over. But let's talk about solutions. You guys should actually recognize this chart from the very beginning of class, early on in the semester, when we were talking about how to classify matter as a mixture or as a pure substance. We looked at this chart. So solutions are way down here at the bottom. They are a type of mixture. There's multiple things in a solution. It's a homogeneous mixture, not a heterogeneous mixture, homogeneous. So that means things are mixed evenly. My favorite example of a homogeneous mixture would be like vanilla ice cream. There's multiple things in ice cream. There's sugar, there's milk, there's water, but every bite tastes the same because it's mixed evenly, and that's a solution. But there's 2 different types of homogeneous mixtures that you see, a solution or a colloid. I bet you've never heard that word before. What is the difference? It all just has to do with how big the particles are. Okay, so colloids have bigger particles, solutions have smaller particles. So if we actually define a solution, it is a homogeneous mixture, and the size of the particles, they can be ion sized or molecules. Specifically, I'll say small molecule size particles. So this table is a good example, gives you a few more numbers, kind of some more concrete examples too. Solutions, they have the smallest particles. Particles in a solution are less than 2 nanometers in diameter. Do you guys remember a nanometer? Anybody remember how many nanometers are in a meter? There's a lot. More than a million. Okay, Gliana got it. A billion. Okay, 10 to the 9 nanometers in 1 meter. So incredibly small size particles in a solution. So small that you cannot filter them out. Okay, run them through a filter, nothing's going to separate out. They're just too small. Solutions tend to be like you can see through them. They're transparent to the light. So you've dealt with solutions like when you come into the lab and you have bottles, dropper bottles and things. You can usually see through those things. They may be colored, but they're translucent. All right. So a couple examples are atmosphere, mixtures of air, seawater has salt in it, and other things as well. Oxygen, and then gasoline and colloids. Though the particles are a little bit bigger. However, these don't filter either. I mean, milk, unless you let milk sit in your refrigerator way too long. Anybody ever taken a drink of milk that has been there a little too long? I promise it's going to happen to my husband one day. Any of you drink straight from the carton? Why do you do that? Don't do that. Just grab a glass, okay? He does that. You don't like milk? Anyways, milk could become something that you could filter, but it's not supposed to be that way, right? That's gross. And then heterogeneous mixtures. These have particles that are huge, 500 nanometers, which is still really small, but compared to solutions, it's 500 times or 250 times bigger. So my favorite example of a heterogeneous mixture would be blood. Let's think about blood for an example. Anybody know your blood type? You should. Okay, what's the universal donor and acceptor? Anybody know those? Universal donor, you can donate your blood to anybody. Yeah, O negative. I'm O positive, so almost, but not quite. Yeah, me and Autumn are both O positive. And then the acceptor, AB positive. So yeah, you should know your blood. You should donate blood. if you can. But think about blood. What's in blood? Why could we filter out blood, or why would it separate upon standing? Okay, yeah, Allie says it, plasma. This is actually the largest component of your blood. Over 50% of your blood is plasma. Keegan, yep, red blood cells and white blood cells. These are the things that if you just have some blood in a container or a bag and you leave it in the fridge or whatever, those things will settle to the bottom. You also got platelets. You have electrolytes. You've got oxygen in your blood. Okay, these things are smaller. My handwriting is really good today. So these things, if you filtered out all the red blood cells and the white blood cells and the plasma, you could actually call blood then a colloid or a solution, okay, depending on what was left. But when you have everything in your blood the way you should, you got sugars in your blood, right? Sugars are larger molecules. So there's actually all types of particles in blood that would make it different things if you filtered certain larger pieces out. But anyways, all right, so if we're looking at a solution again, kind of over, we've defined it, it's a homogeneous mixture, but there's two parts inevitably to every solution. So the first one is the solvent. This is present in greater amount, okay? There's more solvent than there is solute. Okay, so the solvent is usually a liquid, but not always. And that's what we're dissolving something in, okay? It's a liquid typically that any sort of gas or solid is dissolved in. So this is, there's more of it, okay? There's more solvent than there is solute. And then the solute is what you're dissolving in your solvent. And I really like this table right underneath because we typically think a solution is just some sort of liquid dissolved in water, like salt water. You know, if I said, what's a solution? That's probably the first thing you'd tell me. But there's so many more examples. And I like this table because I think it kind of expands your idea of what solutions are for a minute. It could be any physical states of matter, not just a solid and a liquid. You could have gases mixed with gases. You see different examples here. A gas and a liquid, you guys can think of that. My favorite drink ever, seltzer water, okay? Especially the unflavored kind. CO2 dissolved in water. Okay, gas in a solid, that's weird to think about, but you could have a solution of that. Liquids mixed together, gasoline is a prime example. So that's also a unique example of a solution. The one we tend to think about is a solid and a liquid a lot, right? But you can also have solids mixed together, okay, to make different metal alloys. So there's all different kinds of solutions. So don't box yourself into thinking, oh, it's just some sort of solid particle type matter dissolved in a liquid until I can't see it anymore. Many other examples, okay? So if I ask you on the exam, give me 3 unique types examples of a solution, okay? You should be able to name a few examples like this or identify a few, okay? All right, everybody got that? Any questions before I move on? All right. So now that we've defined what a solution, so that's the first big thing we did today. We defined what a solution is. Now we're going to talk about how do we know when something will dissolve, okay? Just because you mix things together doesn't mean that you're going to get a solution, okay? Not every single solid or every single gas or liquid could be dissolved in every liquid. Okay, so there's rules and there's guidelines. Almost remember the solubility rules and guidelines. There's times when things are soluble and there's times when things are not. Same idea here. What determines solubility? Fortunately, I'll tell you, we're not bringing solubility rules back. Okay, it's not going to be part of chapter 9. Don't forget them though. So there's a kind of a motto or a mantra I want you to memorize as you learn to predict these things, and it's this right here: like dissolves like. Like dissolves like. Okay, what does that mean? It means, well, we can kind of unpack this with these 3 examples below. Like dissolves like. So we're talking about polar things and nonpolar things. Polar solutes, polar solvents, nonpolar and nonpolar. When you have polar or ionic solutes, the thing you're dissolving, those will dissolve in polar solvents, okay? Remember, things that are not ionic, okay, so covalently bonded compounds, those are two nonmetals, right? Ionic compounds are a metal and a nonmetal. Remember that. But anything that's polar or ionic, those kinds of solutes will dissolve in polar solvents. The example given is salt and water. So Na, this will dissolve into its ions. This is ionic compound. And then water. What do we know about water? Is it polar or nonpolar? Well, obviously the example here is indicating that water is polar. So we could draw those dipoles in. They're pointing the same direction so they don't cancel. So that's why you would get a solution here. All right, what about the next example? Nonpolar solutes will dissolve in nonpolar solvents. Oil and gas, those things will mix. Those will give you a solution. And then lastly, if the first two are true, then the third one's also true, that polar solutes do not dissolve in nonpolar solvents, and vice versa. Nonpolar solutes do not dissolve in polar solvents. So anybody make your own salad dressing? You do like a oil and vinegar type salad dressing? I hate them. I mean, I like them, but I hate them because you gotta like shake the bottle really hard before you can dump it on your salad, or you're just gonna get oil, or you're just gonna get vinegar. Because they don't mix, okay? You have to physically force them to try to mix and then quickly pour it on your salad before they unmix because they just don't make a solution, okay? Because one is polar, one is not. I love Italian dressing. Who loves tzatziki dressing? I'm sorry, that's like the best there is. If I could drink it, I'm just kidding, that's gross. But their tzatziki dip, that stuff, if somebody challenged me to get a whole container of it with just a spoon, I think I would, if I was paid to do it. All right, I'm going to launch a poll question here. I want to make sure you guys see how well you understand this. So let's think about this. Olive Garden. Who goes to Olive Garden anymore? People still go to Olive Garden? Maybe for their breadsticks. Okay. And you're not old. The best is the house from US Pizza. Guys, there's so much better pizza than US Pizza. Maybe that's controversial to say, but I don't know. All right, here's the question. Based on the concept, like dissolves like, which of the following solutes would dissolve in acetone? Okay, acetone's like fingernail polish remover. And I'm going to draw this out so you can see what acetone looks like. CH3. You got a carbon. Okay, oxygen parentheses. So it's branched off the carbon. And then you got another CH3. So I know what y'all are thinking. Oh, this is symmetrical, but we got to draw the dipole in. I got one dipole right here towards that oxygen, and it doesn't cancel with anything. I don't have one pointing down. So think about acetone. Is it polar or non-polar? I got a dipole here, doesn't cancel. So based on that, now look at these options and think, okay, which one, if acetone is polar, then you need to pick the compound on here that is ionic or polar. If acetone is non-polar, you need to pick a compound that would be non-polar, because that's the way the like dissolves like principle works. Okay, maybe the ranch from US Pizza is good, but I say the ultimate ranch is from Wingstop. Wingstop has really good ranch, and their fries are really good. Okay, so good ranch, good fries, and their wings aren't bad either. Domino's is the best. I used to sell that stuff to people in buckets. Keegan, you worked at Domino's? And you sold buckets of ranch?
No, I worked at US Pizza and sold that.
Oh, US Pizza, okay. All right, well, I can't knock it unless I've tried it. Okay, so we've been going for over 2 minutes now, so I'm going to close the poll. Only 52% of y'all voted. Get your votes in. I haven't been to Brick and Forge yet. Is that place good? Y'all been? It's kind of new. Uh-oh. Uh-oh. We have controversial ideas here. No, that place is nasty. Yeah, I miss Old Chicago. Old Chicago's good. All right, I'm closing the poll. Y'all are all gonna make me really hungry before lunch if we keep this up. Okay, most people picked NaCl, and that's what you should have picked, okay? That's the only one that's ionic. All the other things are non-polar, so acetone is polar. And let's look at NaCl as ionic, obviously. Why the second most popular answer was C2H6. Why didn't that work here? Anybody? Yeah, Matt says it's non-polar, okay? That's right. So C2H6, it's just carbon and hydrogen bonds, nonpolar. CH4 is nonpolar. And then obviously a chlorine molecule is nonpolar because two identical atoms bonded. So all the other options are nonpolar. So the correct answer there was NaCl. Because it's ionic. Ionic things or polar things dissolve in polar solvents. Okay, if you're on a budget, go to Little Caesars, but there's so much better pizza here. I'm not saying it's terrible. I'm just saying there's better options. Don't get offended. Okay. Solubility. So in case you're still wondering, I don't understand the like dissolves like. Here's a visual picture. I'm going to read this statement. A solid will dissolve in a liquid when the solute solvent intermolecular forces. That's a huge phrase. I'm going to highlight this. What does that mean? That means the kind of forces between the interactions between your solute. So it's like this picture right here. Oh, I'm on highlighter. This picture right here. You see the red dotted lines? If those types of forces between solute, I can't read the chat right now. I'm trying to teach everyone. If the types of intermolecular forces between solvent and solute are the same as just your types of interactions in your pure substances, then the things will mix. You'll get a solution, okay? But if they're not the same, then they won't mix, okay? So if this is both if these types of interactions are nonpolar and these are also nonpolar, okay, then they'll mix and you have the same kind of interactions between the solute and the solvent. But if one's polar and one's nonpolar, they don't. That's just a visual of kind of what we said above with the like dissolves like, all right? And then down here, when a liquid is soluble in another liquid, two liquids, so you have a solution of liquids, we say those liquids are miscible. So going back to our whole salad dressing debate, vinegar and oil are immiscible liquids. They don't mix, okay? Vinegar and water are miscible liquids. They do mix, all right? Okay, questions on this? Questions on like dissolves like. Now I'm going to really put you to the test, I think. Yeah, we're going to do a practice problem. All right, I want you to look at these three examples. Will the following solutes, so the first one listed, I'm going to highlight these. These are your solutes. And I'm actually going to make an edit. I had a typo on this. Instead of CH2Cl2, we're going to do CH3Cl. Oh, yeah, sorry, let me go back up. So I'm going to launch a poll question in just a minute. I think, wait, did I have a poll question? Let me look. Let me look. No, we already did that one. The next poll question is a problem later on. All right, are y'all good with this slide now? Okay. All right, so will the following solutes dissolve in the following solvents? So look at the first one. You got CH4 and you got water. If it helps you, draw up the Lewis structure and then write out this is polar, this is nonpolar, this is ionic, this is, whatever. Keegan says no. Is he right or is he wrong? So CH4, let's think about this. Just carbon hydrogen bonds here. This is methane. Right? Yep, Keegan says he's right. Of course he's going to say he's right. This is nonpolar. And then you got water. We actually already drew water up above. We know there are dipoles in water. You draw them pointing towards the oxygen. So guess what? Water's polar. So polar and nonpolar? No, these will not mix. Keegan was right. All right, next one, MgCl2 in acetic acid. So you have the acetate ion with an extra hydrogen, makes it acetic acid. And you have MgCl2. So what kind of molecule is MgCl2? Or is it a molecule? Or is it an ionic compound? What do y'all think? Summer says ionic. Keegan says ionic. It is ionic. How do I know that? I got a metal. Magnesium is a metal. It's main group 2. Chloride is a nonmetal. When you have a metal and a nonmetal, you have ionic. So you're going to have ions here, Mg2 plus, and you've got 2 Cl minus anions. So this is ionic. And acetic acid. Here's what acetic acid looks like. Got 2 carbons. You got another carbon. Got the oxygen branched off, and then oxygen here. And there is your, I'm actually going to draw this bent because the geometry of it would be bent. So draw it like that. You got these lone pairs here. So you got dipoles all over this, right? One pointing towards the oxygen, one pointing there, another pointing there. So this is definitely polar. Acetic acid is a polar solvent. So will MgCl2 dissolve in something that's a polar solvent? Yes. Good job. Okay. Bradley says, so why? It goes back up here to this kind of picture. The type of intermolecular forces at play, Bradley, between magnesium and chloride ions match the type of forces at play between molecules of acetic acid. Okay, so here would be like your Mg2 plus and then your Cl minus. You have ionic bonds here. They're pretty strong, but when you dissolve ions, okay, you've got charges, you got separation of charge because this has a plus and this is a minus. And then you got a polar solvent. So we could go back down here to this. So we could draw in the partial positive on the carbon and hydrogens, and we could draw the partial negatives in on these oxygens. So again, you got separation of charge, right? So when you got things that are charges, obviously the negative portions on this are going to be attracted to an Mg2 plus. You see the positive here and the negative, there's going to be attractions there. And then in the chlorides, Cl minus, they're going to see these partial positives. There'll be attractions there. Does that make sense? When you have any kind of separation of charge, even if it's a partial separation of charge, which is why you get polar molecules, those are attracted to the positives and the negatives on ionic compounds. Same kinds of interactions, all right? So here you'd have partial negative and partial positives, and those are the same types of interactions and forces at play, so that those things will mix. I hope that is a decent enough explanation. I could definitely explain further if. Yep, Keegan, ionic and polar soluble. That's what we said. Let me scroll up. That's what we said right here. I'm going to highlight it. Polar and ionic dissolves in polar. Okay. Yeah. Okay, good. I think it's clicking for some. Let's keep going though. We got one more. All right, CH3Cl in methanol. So you got to ask yourself, what kind of molecule is CH3Cl? What kind of molecule is methanol? If they're both like polar, great, they'll mix. If they're both non-polar, then yep, they'll be soluble. But if one's polar and one's non-polar, no, they won't. So what do y'all think about CH3Cl? Keegan says polar. I agree. And you know what? Some of you may be way more comfortable doing this with an electronegativity chart in your hand. Okay. At this point, I've seen those numbers enough to know which bonds are polar and which are not. So if you're like, how are they determining this? You just take your time, use an electronegativity chart, calculate the differences in electronegativity for all these kinds of bonds. And then you can easily decide If the electronegativity difference is 0.5 or greater, you know what, that's a polar bond. But we've done this quite a bit. So at this point, I know that that bond's right there is going to be polar. So I got a polar molecule, polar solute, and CH3OH is methanol. And then I'm going to draw this bent as well. And we got two dipoles there, one right there and one right there. Okay, so definitely polar. So yes, these will mix. Okay. I wanted to bring up a really cool example though of why this relates to like health science. Has anybody heard of nanoparticles before? It's kind of like a very researchy word. So I won't be blown away if you've never heard of it. Now, before you dismiss it, because it sounds like a research term, there's actually a lot of frontiers and some really cool science and technology when it comes to treating cancer or some diseases in general. Sometimes you have a molecule that will treat a disease, but that molecule is nonpolar. Okay, so in the lab, scientists create these really amazing new novel molecules, but they're nonpolar. Well, guess what? The body, inside the body, things are mostly polar, okay, except for fats. Fats are nonpolar. So what they'll do is they'll take those molecules that are like their drug delivery molecules, and they'll wrap them in a polar envelope, okay, called a nanoparticle. And then they'll be able to send that anywhere in the body that they want it to go. So they use nanoparticles as a way, if something will not dissolve, but yet it's really great for treating a certain kind of disease or cancer even, they can use envelopes that are the opposite. You know, if something's nonpolar, they wrap it in a polar envelope and then it will dissolve into the body. Okay, so there's a lot of application to this at very higher levels of science that are useful for health and treating all different kinds of things. So I just wanted to mention that because some of you may be thinking, and how is this relevant to me? Don't tell me if you're thinking that. All right, so I'm going to give you a quick list, just a very short list of common polar solvents and common nonpolar solvents. So that if I ask you on a quiz or on an exam, and you should expect that, if I ask you questions similar to what we just did, you know, will this, here's a solvent. Which of the following solutes will dissolve in it? If I ask you a question like that, you could come to this list and quickly look at it and say, oh, this solid, without drawing out the Lewis structure and taking extra time, you could say, oh, I know this solvent's polar or non-polar. So let's think about some common polar ones. Water, obviously. Acetic acid. Pretty much all three on the previous slide. Methanol. Okay, these are all polar. And there's many more than this, but I'm just giving you a few. If you want the structures for these, just look at the previous slide. We actually drew them out. But some nonpolar solvents that we haven't looked at is carbon tetrachloride. So the carbon chloride bonds are polar, right? But there's symmetry in this molecule. So all the dipoles cancel, which is why overall this solvent is nonpolar. There's one called diethyl ether. So this looks like this. You got CH3, CH2, and then you got an oxygen. And then you got the reverse, CH2 and CH3. So again, there's symmetry here. So this molecule is nonpolar overall. And then you might have even heard of this before, benzene. This is C6H6. All carbon hydrogen bonds there. So these are three really common nonpolar solvents. Okay. Anything in addition to methanol, like ethanol, propanol, you may have heard those words before. Those are also polar, but I'm not going to give you too extensive of a list. Okay, everybody got that written down? So what have we talked about so far? We defined what a solution is. And then we started to understand the guidelines of predicting solubility, like when is something going to make a solution or not, with the like dissolves like. Now we're going to look at the fact that solubility has limits. So if something will dissolve, great, but we can probably only dissolve a certain amount of it. Okay, eventually you're going to reach a limit, or you've got a certain quantity of your solvent and you've dissolved all the stuff you can dissolve in it. It won't accept anything else. So we call that a solubility limit. With salt and water, there's a limit here. I think I'm going to misquote this. Somebody actually should Google this and help me out. There's somewhere between 30 to 36 grams of salt, NaCl, that you can do, and it's either per 100 milliliters or 1 liter. I know that's actually a large difference in volume, but I can't remember if it's per 100 milliliters, maybe? Somebody Google that. Is it per 100 milliliters or per liter? That's the solubility limit of salt. So the idea here is that there's a limit to how much solute can be dissolved. Past the 30, 35 gram mark of salt, you just can't dissolve any more salt in that amount of water. I don't know if it's 100 milliliters or 1 liter. So we call this the max amount of a solute that can be dissolved. That is what we're calling the solubility. So if I say the solubility of sugar in a certain amount of water, or the solubility of CO2 in a certain amount of a liquid, then we would express that in the units of, that's the next point, we would express that in units of grams of the solute. That could be the sugar or the salt or the CO2. It is 1 liter. Okay, I knew it. So units of solubility, though, they're not what we wrote up here. It's grams per 100 ml. That's what I thought maybe initially. It's always gram per 100 ml. And per 100 ml of solvent, that is. We're actually going to work a problem later where we use units of grams per 100 ml. And this is deceiving because this is the first time we've ever had a number, which is actually just part of our unit. So when we work the problem later with units of solubility, you will not divide by 100. You're going to treat 100 as though they're just more letters and that it's not a number. That'll make sense when we actually work the problem with Henry's law in a minute. Okay, last point on the slide. Once the max amount of solute is dissolved in a given solvent, the solution is said to be saturated. Once you have dissolved all the solute you can dissolve, and you can't dissolve any more, maybe you're adding more to it, but you see it's not dissolving, that solution is saturated. You guys are actually all familiar with saturated solutions or even super saturated solutions. I'll give you an example. Anybody ever bought a container or a jar of honey before? And you use all the honey and it kind of gets to the bottom and then it just becomes really gummy and sticky and like crystallized, and it's like not a liquid anymore. It's like you can see the sugar in it. Nobody's shaking their heads. You've never, okay, thank you. Yeah, that happens with honey a lot. So there's a lot of sugar, obviously, in honey because it's sweet, but there's more sugar than the honey can actually handle. So some of it will like crystallize out in low volumes. And what can you do to get that sugar to redissolve? What could you do? You guys know. You can put it in some warm water. Okay, you can microwave it, heat it up. If you add heat, you can manipulate solubility, and we're going to look at some rules and examples of that. So this is a picture, though, a visual of how things dissolve. This helps my mind see what molecules are doing when we talk about something dissolving. If you look closely, we got these sodium cations and chloride anions are the green spheres. Sodium cations are the purple. And then you got these molecules of water, which is the red and the white. Remember ionic compounds, that they're very ordered and arranged. We call them crystalline solids because the cations and the anions arrange themselves in a unique pattern. So if we're going to dissolve this, we're going to call this a salt crystal. If we're going to dissolve the salt crystal into its ions, what actually happens, and we don't see this because the molecules are so small, but the water molecules come along and they bump into the salt crystal. And if you get enough interactions, I really want to try to zoom in. If you get enough interactions, say between that cation and the water molecule, or between this anion and the water molecule, it will literally carry it off and it'll surround it. And this one is dissolved. All right, it'll kind of break it off of the crystal and carry it away. And then the same thing you see with the sodium up here. It's that ion is now dissolved. Okay. So when something is soluble, that's actually what's happening. If you're an ionic compound and you can break up into your ions. Okay. Everybody got everything off this slide? So the big thing here were units of solubility, gram per 100 ml, and understanding what a saturated solution is. And why would you want to add water to your honey? Is that what you were saying? Get the sugar to dissolve by adding water? Maybe it could work if it was hot water. All right. Next thing, I want to ask you this question. Is the dissolution of a solute into a solvent a physical or a chemical change? What do y'all think? The dissolution of a solute in a solvent, physical. So this goes all the way back to chapter 1 stuff when we were talking about identifying chemical reactions. Is dissolving something a physical or a chemical change? What do y'all think? Keyshawn says physical. Physical, Najee says physical. Yes, that's exactly right. I mean, look at the picture up here. Are we creating anything new, like a new compound? No. In a chemical change, you create a brand new compound. The bonds break and rearrange to give you new compounds. We're not doing that here. We're just breaking things apart. We're not actually creating new things, though. So definitely, I'm going to highlight it's a physical change. Remember that, not chemical. Okay. So going back to the honey idea, when we said if you want to dissolve the sugar in the honey, you just heat it up in the microwave or in some warm water. That is a way you can increase solubility. So we've talked about what a solution is, defined it. We've talked about guidelines and principles for when something will dissolve, like dissolves like, but there's ways we can manipulate solubility, okay? Solubility has limits, and we express those with units of gram per 100 ml, but we can manipulate the solubility with temperature. All right. However, this depends on what your states of matter are. So if you can see we've got two different kind of bullet points underneath this. If you have a solid dissolved in a liquid, the guideline is going to be how you manipulate is different than if you have a gas in a liquid. So let's take the example of anybody drink sweet tea? I was raised in the South, so I kind of grew up on it. I really don't drink it anymore. If you go to a restaurant, you drink your sweet tea, and then the waiter or the waitress comes, and oops, they filled your glass back up with unsweet tea. How many times does that happen? You grab a packet of sugar, and what do? You shake it, and you pour it in your glass of tea. But it's iced tea. Does that sugar mix in very well? You can start with your straw all you want, but that sugar usually like settles down to the bottom. Okay, so if you wanted to get the sugar to dissolve in tea, what would you do to it? Sugar is a solid. Your tea is a liquid. If I wanted to dissolve it, what would I want to do? Lucy said it, heat it up. Okay, so the point is when you have a solid dissolved in a liquid, if you increase temperature, I'm telling you, my handwriting is just really good today. If you increase temperature, you'll increase solubility of the solid substance, the solute in the liquid, which is the solvent. Right? Orchid says just take it back and ask for a sweet tea. Gas dissolved in a liquid. How does that? Let's think about that. So I'm going to use my favorite example of my favorite drink, unflavored carbonated seltzer water, basically club soda. Okay. What do you have? You could think of any Coke, for example. Yeah, it's carbonated, so there's CO2 and it's dissolved in the liquid. All right. So if I have a CO2 or carbonated drink that's in the fridge and I pull it out of the fridge, and then I have one that's just been sitting on my counter at room temperature, which one is going to have more of like a fizz to it? If you open it up and drink it, which one would have more gas dissolved in the liquid? The cold carbonated beverage, or the one that was at room temperature? What do y'all think? Mm-hmm. So everybody's saying in the chat, the cold one, absolutely. So what that means is as you decrease temperature for gas particles, because they have a lot more energy. So if we decrease temperature, we're kind of slowing them down a little bit, and they'll stay dissolved in the liquid better that way. So if you decrease temperature, you increase solubility of the gas in the liquid, right? How does this apply to health science? Have you guys ever heard of like a hyperbaric chamber? Okay, we have oxygen in our blood, right? Sometimes people have issues with their blood pressure. There's different therapies and treatments we can do where you also have to think with gas, pressure applies here. Why are carbonated drinks pressurized? Okay, if you shake them, they could explode. If you freeze them, they explode because they're highly pressurized. And that pressure is also helping keep the gas dissolved. So there's different therapies when it comes to health sciences where people can sit in like a cold room or a pressurized chamber to help treat oxygen levels in their blood. Okay, there's different things you can do there. But I'm going to look at some graphs to help reinforce the idea visually. So if we have a bunch of different solids, we're back to solids and liquids. You're going to have a problem on your homework that gives you, I think, a solubility chart like this, and then it asks you a question about it. So let's look at how to read these. We got all these different solids: glucose, sodium acetate, sodium nitrate, potassium bromide, all these different things. And the x-axis is temperature. So what you notice is that as you increase temperature, the y-axis is solubility, and look, our units are grams per 100 ml. As you increase temperature, what happens to these data lines? They slowly go up, right? So if I were to ask you, what is the solubility of glucose at 10 degrees Celsius? This is the style of question you'll have on your homework. What is the solubility of glucose at 10 degrees Celsius? What you need to do, well, you probably need to zoom in. Trying to zoom in. Okay. Here's 10 degrees Celsius, right? We're going to just take this and connect it right up to which one's glucose? The red was the glucose. Okay. And then you would walk that over to the x-axis. Okay. And we say, okay, here's the solubility, because that's what the y-axis measures. So what number is that? Well, this one's 70. So it's between 60 and 70. So you'd say the solubility of glucose is, maybe 65, somewhere around that. 64.5, 63 grams per 100 ml. Okay. So that's how you read a chart. If I said, what's the solubility of potassium bromide at 50 degrees Celsius? Okay, you do the same thing. You start at the x-axis, find that temperature, walk the line up to hit the data line, and then walk it over the x-axis, okay? And again, this reinforces the idea that as you increase temperature, solubility of any solid in a liquid is increasing. Okay, questions on this? Sometimes it may say, at what temperature would you achieve a solubility of 80 grams per 100 ml? Okay, at that point, you're just trying to find, you find that solubility, walk it over the data line, and then walk it down to the x-axis to see what temperature that corresponds to. All right, let's look at gases. Okay, we got CO2, oxygen, nitrogen. You notice the opposite trend here. As you increase temperature, solubility of the gas decreases. There are slightly different units here. This is mmol is a millimole. We actually have never seen that before. Millimole per liter. It's still conveying the same idea. A quantity of your solute, which is the gas, per volume of solution here in liters. Okay. So just most of them, the trend is downward, okay? As you heat things up, gases do not stay dissolved in liquids. Questions on these? I really don't have a whole lot else to say. I just wanted you to see these and explain a little bit. Okay, now we're going to work a problem. So get your calculator. After I explain Henry's law, we're going to work a problem on Henry's law. Henry's law is going to relate pressure and concentration of gases. So it's kind of another gas law, but it has to do with solutions. So that's why we didn't introduce this with the other gas laws. It says the concentration or the solubility of a gas is directly proportional to the partial pressure. What is a partial pressure? So think about if, like our atmosphere, you've got all different kinds of gases in the atmosphere. When you have a mixture of gases, every individual gas exerts its own unique pressure. So we call that the partial pressure. Okay, the gas for that, or the pressure for that unique gas. The concentration or solubility of a gas is directly proportional. So that means if one increases, the other increases. If one decreases, the other decreases. Concentration solubility is proportional to partial pressure of the gas when temperature is held constant. So let's actually look at the numbers and the variables for the law to understand this further. It says, in other words, we could say pressure affects the solubility of a gas in a liquid. How so? If we increase, they're proportional, right? So if we increase pressure, we increase gas solubility. If something is proportional, then as one increases, the other also increases. So that's Charles' law, Gay-Lussac's law. Remember, Boyle's law was the only one that was inverse, pressure and volume. They had an inverse relationship. So here's what Henry's law looks like. It looks a whole lot like Charles or Gay-Lussac's or Avogadro's law. You've got C1 over P1 equals C2 over P2. So C is the term for concentration. What is units of concentration? Okay, we said up here in the definition, we said concentration or solubility. So our units for solubility, and here, concentration, are gram per 100 ml. Okay, that is all the unit. We're not actually going to divide by 100. We're going to treat it as the unit. For you visual learners, here's another picture. Remember, we did this a whole lot with Charles and Gay-Lussac's law. If you have a container that has a movable lid, here's what it's trying to show you. The blue is the liquid. The red are the gas particles moving in and out of the liquid. So you've got this equilibrium where the same number of gas particles moving out of the liquid match the same number of gas particles moving down into the liquid. Okay, so it's at equilibrium. Some of you missed this on exam 3. Equilibrium does not mean equal numbers or concentrations of reactants and products. It means equal rate of forward and reverse reaction. Okay, and that's what you see here, equal rates. If we increase pressure, so Henry's law addresses this. If we increase pressure, we're going to force, look, we got a lot more down arrows. We're going to force a lot more of these gas particles down into the liquid, okay? This is what happens at smaller scales in hyperbaric chambers, or where you sit in like a pressurized room and we're increasing the amount of gas in, say, our blood or oxygen in our blood. And then eventually we'll restore equilibrium, okay? But notice now we got a lot more gas in the liquid than we had starting out. Okay. So now we're going to work. Everybody good with this slide? Let me stay here for a minute. We're going to work a problem. So when the solubility of oxygen is 159 mmHg, you guys remember what that units of what? mmHg. So it says when the P of oxygen, P is the partial pressure of oxygen, and when it's 159 millimeters of mercury, that's units of pressure. Oh, Keyshawn, you want me to go back? I'm going to leave the problem visible so people can read it. When the partial pressure of oxygen is 159 millimeters of mercury, the solubility of oxygen in blood is 0.44 gram per 100 ml. There's our units of solubility. what is the blood solubility at 11,000 feet elevation where the partial pressure of oxygen is 56 millimeters mercury? Just like I would encourage you to do on like a combined gas law problem, you need to go through and highlight and annotate. So we've got a pressure here and a pressure here. So I'm just going to label these P1 and P2. And what's nice is that we have the same units on both. Keyshawn, were you good with this slide up here? Hopefully, maybe. Okay, I hope you are. Let me know. And then we have a concentration given to us. Okay, so here it is right here. So that is C1. And it says, what is the blood solubility? So we're looking for C2. So our equation is C1 over P1 equals C2 over P2. So we're just going to plug everything in. So 0.44 gram per 100 ml over, that's C1, 159 millimeters mercury. We're looking for C2 over 56 millimeters mercury. Now we're going to solve for C2. So you multiply both sides by 56. Cancels on that side. So you do 56 times 0.44. Do not divide by the 100. Keep that as part of your unit. And then you do divide by the 159. Grayson has a great question. What does the 11,000 feet elevation have to do with anything? Why are we not using that number in the problem? This is a good question. Anybody have a thought on this? Anybody know why it includes 11,000 feet elevation?
Does it help get rid of like other variables in the problem to help keep the like equation constant?
It doesn't help necessarily get rid of anything. It's just relating the fact that as you increase in elevation, pressure decreases. Remember when we were talking about atmospheric pressure and I introduced you the term of what an atmosphere is? We said at sea level, you have 14 psi, 14 pounds per square inch of atmosphere pushing down on you. But as you go up in elevation at the top of a mountain, okay, if you go to Colorado or you're 2 miles high or whatever, you have less of the atmosphere pushing down on you. So the pressure is inherently lower at higher atmosphere. So Grayson, that number does not actually play into our equation anyway here. It's just illustrating that as you as you increase in elevation, pressure decreases. And that's where we get our new P2, which is obviously lower than P1. Does that help? Okay, anybody get the answer? Kendall, Danielle, okay, good. Y'all got 0.1549 or 155 gram per 100 ml. Good, you got the units. So those are units of solubility. That is C2. That's what, so we went down, we're roughly a third. So pressure decreased roughly a third. So that means solubility decreased by a third. So I don't know what like your pulse oxygen should be, like what your percentage of oxygen, like how low can our concentration of oxygen in our blood go before we just can't survive at that low concentration. But that's why a lot of times when you ascend in elevation, you've got to take extra oxygen with you, or it's why airplanes always have oxygen masks. How many of you always fear when you get on an airplane that you're going to have to use your oxygen mask? Because you'd be at such a high elevation that you would need extra oxygen to survive. Okay, so that's Henry's law. All right, what we're getting to now, anybody need me to stay here for a second? So what we're about to get to, let me preface, is probably the most important part of today's lecture. So the last 15 minutes, we're going to talk about units of concentration. This is really important. The whole pharmaceutical industry depends on units of concentration. Anytime you take a medication or a drug of some kind, it has units of concentration. It has to. We have to know how much to take. So please pay attention. You really are going to use what we're going to talk about next moving forward if you choose to stick with a health science profession. All right. Concentration. I briefly introduced this in chapter 7, but we're going to dig into it now. Concentration is just an amount of solute per volume of solution. Okay, amount of solute per volume. So any medication, especially like infants medication, obviously kids can't really swallow pills, so it's delivered in a liquid form. In hospitals, we deliver IVs, okay? We have to administer things in liquid form a lot of times. So this is why concentrations for solutions are critical. So weight volume percent is one way we can convey concentration. It's also called mass volume percent, or you'll see it abbreviated WV percent. Molarity is the other way. So let's fill in the blanks here. Weight volume percent is going to be grams. That's the amount of solute per milliliter of solution times 100. Molarity is different. The quantity of solute is going to be moles of your solute per liter of solution. So you got weight volume percent, grams per ml. Do not forget the times 100. That's how you turn it into a percent. And then molarity, which is just abbreviated with an M. That's moles per liter. Nurses, anybody who wants to be a nurse? I remember when I would have to go in when I was pregnant, you always have to give a urine sample, and they look at those and they can tell a lot of things about you and your health from urine samples, but they use concentrations of moles or molarity, for things like urine samples. So, all right, let's talk about how to prepare a solution real quick, and then we're going to spend the rest of the time working problems. There is a proper way and an improper way to prepare any solution. Here's why. The final volume of the solution, which is the combination of, okay, I'm going to go back up. Pause. We'll be right back. Are you good? Okay. Okay, the total volume of a solution, which is your solute and your solvent, it includes both, what I just said, solvent and solute. And your solute also has a volume. We have to account for that. If I said make me 1 liter of a 10% sodium chloride solution, and you get the necessary amount of sodium chloride, which is salt. If you fill up your container to 1 liter and then you dump the salt in, you're making it all wrong. Here's how you do it. First, step 1 is you take your container. Here we have this volumetric flask, and you add the solute. Okay, here their solute is this yellow powder. So the first thing you see them doing is dumping this yellow powder into the volumetric flask. The second thing they do is add some, but not all, some solvent. What does this do? This dissolves the solute. Okay, so if we need 1 liter, we're going to add maybe 500 milliliters or 800 milliliters. We won't add the total volume just yet. Lastly, you're going to fill to final volume. That's a U with solvent. Remaining solvent, okay? Fill to the final volume of solvent. So you add your solute, you add some solvent, and then you add enough solvent to get to your final volume. That way, you don't go over what the volume should be, and you don't mess with your concentration. Okay? You get an accurate concentration this way. So if I ask you on an exam or something, describe to me how to prepare a solution of, 50% glucose or whatever. I would expect it in this order. You would list these briefly. You don't write me a paragraph. You just list these steps in this order, okay? All right, so now we're going to work problems on concentration. I got one more poll question that hopefully we will get to in the next 10 minutes. Everybody good with this slide? Okay. Oh, I forgot this one real quick. Remember earlier that I mentioned we need different kinds of solutions, like solids dissolved in solids and gases dissolved in gases. You're going to have, there's a problem in the textbook that I think is a really phenomenal problem. It's about Listerine. Okay, one of the active ingredients in Listerine is alcohol. Okay, alcohol is a liquid. So Listerine's a liquid, that's the solution. Alcohol is a liquid, that's the solute. And if you have, that's what it's talking about down here. If you have some sort of solution that is one liquid in another, alcohol and Listerine, what are the units for that? We can't use gram per ml because we have two liquids. What are units that we use for liquids? It would have to be ml of solute per ml of solution. Okay, you got to use units that represent liquids in both cases if you were trying to express a weight volume percent. Actually, it would not be weight volume anymore. It would be volume per volume, right? But same idea. What if we have a solution of solid in solid? There, it's a weight per weight percent, which would be grams. I'll just do G for grams. Grams solute. I know I'm moving really fast right now. I'm going to stay here for a second. Times 100. All right, there it is. So just keep that in mind, especially when you go to work that Listerine problem. You got to use this equation right here. That'll be on my recommended textbook problem list. Gases, Keegan, we can use units of milliliters or liters for gases. I can't think of an exact problem that's like on your homework or in the textbook where it does give you, you know, a gas is all another gas, but it would specify what units probably it would need you to use for that question or a problem like that. It's a good question though. Okay, in all of our gas laws, we use like liters and milliliters to express volume of a gas. All right, here's our equation for weight volume percent. We're going to work some problems using this equation. So number one, what is the concentration in weight volume percent of 15 grams of glucose dissolved in 100 milliliters of solution? So we have weight volume percent equals 15 grams. I'm going to use capital G for glucose per 100 milliliters of solution. And don't forget the times 100. So what is our percent? Grayson says 15. That's exactly right. Honestly, the hundreds cancel out, don't they? So that kind of makes it nice. Should be 15%. Good. So that one's fairly easy. Let's do a harder one. If I dissolve 180, look at the units here, milligrams. So what are we going to have to do before we plug this in? You're going to have to convert milligrams to grams. So if I dissolve 180 milligrams of heparin, what's heparin? Anybody familiar with heparin? Into 15 milliliters aqueous solution, what is the weight volume percent? Heparin's involved in your blood clotting system. Is it more like a blood? I can't remember if it's more like a blood thinner. It prevents clotting, or if it aids in clotting. But I know it's involved in that cascade. It's a blood thinner. Yeah. Okay, so let's do 180. Y'all remember how to do this? How many milligrams per, oh, Keyshawn already throwing the answer out. Milligrams to grams. So for every 1 gram, it's 1,000 milligrams. So that should equal 0.18. Well, I didn't have to write that last zero, but grams. Okay, we got milliliters for the bottom. That's good. So now we just solve for the weight volume percent. equals 0.18 grams of heparin divided by 15 milliliters times 100. Did y'all get 1.2%? Seems like it. Okay, if there's no debate then. So these problems are nice and relatively easy because you're just plugging everything in on one side of the equation and solving exactly how the equation says. So I'm going to give you a harder one. I actually have a poll question on this. So in the remaining 5 minutes, how many grams down here on this next slide of NaCl are needed to make 0.25, look at the units, liters, whoops, 0.25 liters of a 1.5% weight per volume saline solution. So here you're given the percent and you're given the volume, although it's not in milliliters, and you're solving for the grams. So you need to rearrange your equation. Don't forget the 100. And I'm going to launch the poll question where I want you to put in your answer. So I want you to wrestle with this for a minute and then we're going to work it. Oop. All right, I'm going to start working this. So I'm going to plug in my 1.5%. That equals grams, that's what I'm solving for, per, we got to convert liters to milliliters. So 0.25 liters times, for every 1 liter, it's 1,000 milliliters. You should get 250 milliliters. 250 milliliters, it goes on bottom, that's times 100. So what do I need to do to solve for grams? I need to cross divide both sides by 100. 100 cancels on the right side. I need to cross multiply both sides by 250. If you're wondering how the units work out here, remember it's weight volume percent. So it's actually a gram per ml percent. All right, we don't technically write the units in gram per ml percent every time because that's inherent in the name weight volume, but the milliliters will cancel here and leave you with just grams. So you should do 250 times 1.5, which should be 375. Divide that by 100. You should get 3.75. Oh, now you're all putting your answers in. I'm ending the poll.